Okay, so here we have to remember that we have a property that if the radicals are the same, these are 4, the index is 4, and they're both the same, I can multiply these together. So 27 times 3 is 81. And it just so happens that 81 is a perfect fourth. So the answer to this one is 3. Over here, I have to get the radical out of the denominator. And so this should look a little familiar. I've got a 5th root. So I need to multiply by the 5th root of 8. Okay, because then this gives me, when I multiply the top, I have the 5th root of 24. And on the bottom, I have the 5th root of 32, which again, that 32, this gives me the 5th root of 24 over 2. All right, lastly, we want to multiply this by the conjugate. And of course, you have to remember too that whatever you put in the denominator, you have to put in the numerator. Because this is the same thing as multiplying this by 1. All right, so I'm going to multiply the top. 3 times 6 plus the square root of 2. And on the bottom I have 6 squared, which is 36, minus the square root of 2 squared, which is 2. So now this becomes, I'm going to distribute this 3, so this becomes 18 plus 3 times the square root of 2 over 34. So that is the answer to that one. All right, adding and subtracting like radicals and roots. Okay, what is x plus 7x? Pretty easy, right? It's 8x. Well, that is exactly the situation we have here, except x is the 4th root of 10. So here I have my invisible 1. I have 1 of these, and I'm adding 7 of these, so I get 8 times the 4th root of 10. Here, I've got 8 to the 1/5 power, which is the 5th root of 8. And I have one here and one here. They're the same, so I can add these together. So I have 12 times 8 to the 1/5 power. Over here I have a different story though, because this is the cube root of 54. This is the cube root of 2. So right now, I can't combine these. But if I simplify this, then you're going to see that it will come down to the cube root of 2. So 54 is actually 27 times 2. So the cube root of 27 is 3. Then I have times the cube root of 2 minus the cube root of 2. So 3 minus 1 is 2 times the cube root of 2. Okay, so now I would like you to try these. And one thing you need to know is that with math, I mean, that looks downright nasty, right? And it looks like it's going to be really difficult. You need to break these problems down into smaller pieces. You're looking at each one of these individually. You're going to simplify this, you're going to simplify this, and see how they come together. But you've got to go slow and be very intentional on how you do it. You can't, well, a lot of these you just can't go fast because there's so much packed into one little thing. So, okay, so go ahead and pause your video and try these. All right, this one's pretty straightforward. I have 5 times the square root of y plus 6 times the square root of y. These two are the same, so I have 11 times the square root of y. Over here, let's look at these separately. I've got 12 times the cube root of 2z to the 5th. So what does the cube root mean? It means that if I have 3 of something in here, 3 of one thing pulls out 1. So I could rewrite this as 2 times 1, 2, 3, 4, 5 z's, the cube root. This tells me, the index tells me, how many of these spits out 1 out front. So I have to have 3 z's for 1 to come out. So this is going to be 12z, this is now gone, times the cube root of 2z squared. So that's that simplified. Now over here, I have z squared already. I can't reduce that anymore because this is a 3, but this is the cube root of 27 times the cube root of 2 times the cube root of z squared. Well, this is a perfect, cube. This is a perfect cube, so this is 3z times the cube root of 2z squared. So now look what I have, 12z times the cube root of 2z squared minus 3z times the cube root of 2z squared. So that part right here, the z with the radical are the same, so I can just do 12 minus 3 is 9z times the cube root of 2z squared. All right, this is one thing, if you're watching this video and you already saw my class, this is one thing that I forgot to show you, and I apologize. The main reason is because I didn't teach this last year, but I also didn't have the kids do their homework online. They did it by hand, and so I was able to see that. But when it's online, it's got to be perfect, so I apologize for that. Okay, when n is odd, when our index is odd, okay, so like this, then it equals x, right? So this is 7 to the 1/7 power equals 5, and so on. Okay, but when n is even, we have to put it in absolute value sign so that we know that we're dealing with the positive one, because we're dealing with two different, a positive and a negative, but we need to make sure that people know that it's a positive that's coming out on the end. So you can see that these are both positive. Okay, so let's look at this. Look at these two for a second. Okay, so we have the cube root of 64 times the cube root of y to the 6th. So the cube root of 64, this one's kind of tricky because it's a square root too, but it's also a perfect cube, and that is 4. This one, on the other hand, we've got y to the 6th. Is y to the 6th a perfect cube? Well, it is. Okay, another way you can look at this is if I write y to the 6th to the 1/3 power, which is what this is, written in exponential form, okay? If I multiply these two together, I get 6 over 3, which is y squared. Okay, so perfect cubes, we would have y to the 3rd, y to the 6th, y to the 9th, y to the 12th, etc. Okay, and we divide like we do right here. So 6 divided by 3 is y squared. And I didn't have the situation that I showed you in the last slide, so we don't need to worry about that right now. And I am way over time, so I will show you this next one in the next video.